Okay, I guess we'll get started. Thanks for coming. Let me know if you can't hear me well enough. I think it should be okay. This is a talk, again, oriented around the theme of this year about controversial topics. And this is a discussion of deep sources and other things you aren't supposed to see with MEG. So in the MEG world, there has been some controversy about what you can and can't see, and that's changed over the years as technology has developed and we've developed analysis methods and so on. So I'll go through some of the origins of different beliefs about what you could see with MEG and then what we now can see maybe better with modern technology. So the initial belief in the field was that deep sources, i.e. anything below the cortex, could not be seen. And with modern methods and tech, we can now say that this is not true, but this belief still persists in the field. We actually had an intern, Anerta, show up maybe it might have been 8 years ago, who showed us his textbook from undergrad that had a sentence that said deep sources can't be seen with MEG. I wish I had that sentence, it would be good for this talk, but it's still passed around, largely by people maybe haven't been keeping up to date with the field, but it still then prevents people from even trying or thinking they could do an MEG experiment. So it's good for us to advertise that it is possible. So why does this idea persist? There are theoretical reasons based on anatomy. A lot of the initial modeling and so on was based on cortical anatomy. Often things like you can't see deep sources are presented in a contrast with EEG, where you're trying to highlight what you can and can't see with different kinds of technology. Also fMRI is in that context. We also have different MEG technologies, so some of them are better or worse at seeing different things, and so depending on the machine you have, you may have a belief and then you assume that's true for all systems. And of course at the very end, analysis methods haven't been improving over the years so that we have better ways of finding signal that is weaker than what you might see from the cortex. So the first of these reasons why some people think you can't see deep sources, or at least it was thought that way in the past. So the theoretical modeling of the MEG signal was based initially on the cortex, and it was thought that you needed a column of, if I get this on the screen, you needed a column of pyramidal cells all receiving input at the same time for the amount of electrical activity to sum enough to produce an external magnetic field. And so a lot of the modeling work was based on this. And the problem from that is that because the modeling work said if you have strong activity in pyramidal cells, you get MEG work, but then a lot of people made that flip and assumed then that if you see MEG, you must be seeing pyramidal cells. That's not the case. The initial modeling was just saying if you see these, you will see strong MEG. It doesn't mean you can't see anything else, but that has been, I think, was flipped or conflated in people's minds that you had to have one to have the other. We'll be using this idea a little bit throughout the talk. This is called a dipole. So it's a point source of electrical activity pointing in a certain direction. And if you know from physics class that the right-hand rule, you have magnetic field that surrounds an electric current flow in a circle like this. And so if you have a dipole here, magnetic field would surround the current flow and exit and enter the head at certain locations, and that's that activity that we're picking up with MEG. So another reason I think that this idea that you can't see deep sources is what I call a false dichotomy with EEG. A lot of people like to say we can see this with this, we can see that with that, and kind of present it in a very maybe a simplistic manner. So there is a trade-off with EEG and MEG. So with EEG, you don't necessarily have any fall off in the signal. So no matter how deep the source, you could still see a potential difference created by a current flow within a neuron. But the issue with EEG is that even if you can see activity from deep source, that signal as it travels throughout the brain and then interferes with the skull and scalp gets distorted. So it becomes difficult, especially with depth, to tell where that activity came from. In MEG, the magnetic field falls off with the square of the radius, so how far you are away from the signal does affect how strong the source is. So that's another reason that, again, people would say, well, you can't see deep sources. I would say here that we can, it's just that it's more difficult. But if you can make them out, because the magnetic field travels through all those surfaces without interference, you can much better determine where the activity came from. So if you can figure out a way to see these relatively weaker signals, you have a better chance of determining where it came from in the brain. So there's a reason to try to improve our source localization. So here's an example, just as a kind of a somewhat silly, but as a good, I think, example of that you can see deep sources with MEG. This is in fact a heartbeat, so that's obviously deeper than the brain would be. So you can see things at a far distance as long as the signal is strong enough. So really what we have is a signal to noise issue. If the signal is strong enough where you can reduce the noise, you can make out activity at great depth. It really just depends on the signal and then your ability to see it. So you can see those heartbeats in the raw MEG channels. So this is magnetic activity recorded in each of our 275 channels, and you can see the heartbeat in each of these. So another reason, besides I think those first two I mentioned, is that there are technological differences, and this leads to some confusion in the field. The main sensors that we use to pick up the magnetic activity are called gradiometers. A magnetometer on the left is a simpler version, and those are also included in the NeuroMag system, which we do not have. We have a CTF system. So the NeuroMag system, which is a competing company, has sensors that are made up of a combination of some magnetometers like this and some gradiometers like this. And the CTF system only has first-order axial gradiometers that are subbed like this. So what happens is that field in a magnetometer, field comes through this coil. It generates a current in this wire, and then that is read out as an indicator of how much magnetic activity came through that coil. In the CTF system, field comes through this coil, but you notice this one is wrapped the opposite way. So if there's any remaining field from here, it will be subtracted out because this is wrapping the opposite direction. So you end up with a difference between these two coils. So people refer to that as a gradient. A gradient, of course, is somewhat related to a derivative. It's more of the change in current, but it's really a difference with a baseline of 5 centimeters. So it's maybe a bit of a misnomer. It's not really a gradient as you would talk about a derivative, but it's a difference measure between these two coils. So something at depth, as long as it produces a difference between here and here, it may be weak, but you will see some signal. The NeuroMag planar gradiometer, activity would come in one and then go back down through another. So you remember you have these circles of magnetic field. And so you would want to have activity ideally right below this sensor coming up and then coming back down through. The problem is that with that depth, the field is almost going parallel to these. By the time that the big circle comes through here, it's almost going parallel to these, and it barely gets through each of these two channels. So actually, in the NeuroMag system, if you look at modeling, their gradiometers, even though it has the same name, their fall off with depth is much more severe. So if you're used to using that system, you may have an idea that it's really impossible to see deep sources, but it may just be the technology you're using. So this is a model where a radiomagnetometer, the sensor we saw on the left, is used as a control. So it's always, even though this signal would be falling off with depth, this is depth getting deeper this way. We divide by the strength of what a magnetometer would show to make that equal to 1. And you see, relative to a magnetometer, the radiogradiometers in TTF fall off with depth up to 10 or about 9 centimeters here, I guess, but not by that much. Whereas the planar gradiometer in the NeuroMag system falls off quite severely. So some of the idea about not being able to see deep sources is just that gradiometers are not the same. It's the same name, but they have very different properties. Any questions on that? Yep, go ahead.
So if the CTF can see things deeper that are better, why does everyone not use that instead of the other gradiometer system?
Well, that's a good question. So, salespeople come and talk you up, I guess. I'm not sure. There are maybe some advantages. You are doing two different kinds of sensors in the NeuroMag, and you can see here for activity that's very close, you actually get a very strong signal. So if you're interested in cortical activity, it may be a better system. If you are interested in subcortical, you would probably want the CTF. So it really depends what you're interested in, but you should know these facts before you're buying the system. The other thing people like about the NeuroMag, if you go back, is that it's actually easier to interpret the activity in a particular channel. So the peak response will be for activity directly underneath this radiometer. So you can look at the sensor and say the activity directly under there is producing field. I know that. The problem with the CTF machine is that you really, in sensor space, it's very difficult to do your analysis. The peak response actually will be off to the left or the right. So if you have a source right here, it will actually almost look parallel. The circle will almost look parallel to this coil, and you won't pick up much. So actually, the maximum response is off to the left and to the right of this coil. And so it makes it more difficult to interpret in the sensor space. And people, I think, if you were more used to EEG, where you're looking at sensor locations and sensor maps, the NeuroMag system is more pleasing that way. And if, again, you're mostly interested in the cortex, then sure, why not? Thanks. So this is the system that we have here. We have the CTF system with 275 channels. So one reason that we can do a better job now at seeing deep sources and other things is that we have more channels. We have full head coverage. Some of the early systems only had 7 or fewer channels, and you would actually put them over a particular area of cortex, and you would then miss things. So, and again, with those CTF channels, as we talked about, you wouldn't necessarily pick up activity or from even a source directly underneath it, because it could produce its maximum strength somewhere to the left or to the right. So it led to a lot of confusion. We also place the system in a magnetically shielded room to try to block out as much noise as possible, because remember, this is a signal-to-noise issue. We want to reduce noise and increase signal. So we block out activity from around. And in the CTF system, there are 30 reference sensors that live above the helmet. So up in the space above here, you would have reference sensors that subtract out in real time the common noise to all the channels. So it gives you a much better idea of what's really going on in the brain as opposed to outside the room. So analysis methods have also improved. So in the earliest methods, you would assume things about the source. Again, a lot of it based on that early modeling. So if you assume you have a pyramidal activity, then you just model your sources as coming from the cortex. So you don't even try to look for subcortical activity. So that's one thing that happens. So people say, well, if you're not looking for it, you can't see it. It doesn't mean that it doesn't exist. It just means you haven't looked for it. And the other problem is that with the earliest methods, you could really only see the strongest of the sources you have, and the cortex will have the strongest sources. So the earliest method was called a dipole fit, and you would actually try to fit one or more of those single dipoles to the data and say, kind of like doing a regression, fitting a line through your data, you would look for the dipole that best explains your data, and that would often be in the cortex, because anything below that is much weaker. And so you wouldn't see deep sources. It doesn't mean they're not there, you just weren't looking. The minimum norm estimate, that's again developed in conjunction with the NeuroMag system. And there, the most common way to do it is to assume a cortical source and limit all of your search just to the cortex. It actually then projects all of your information onto the cortex, no matter where it came from. It makes it more sensitive to noise, because if you have eye blinks, it's going to put them on the cortex, so you have to try to remove those. If you have subcortical activity, it's going to put them on the cortex, so it really will never find anything but what you're looking for, which is cortical activity, even if it doesn't belong there. So what we use is beamforming, which is neutral to where the source comes from. It's also called SAM, or synthetic aperture magnetometry. You'll see that those names used both used in the literature. SAM was more of a proprietary name by CTF, so some people don't like to use it. It overcomes some of these issues. What it does is it goes through the entire artificial grid of voxels from an MRI, and it generates a unique spatial filter, so a weighting of all your sensors to see activity from that location, but block out activity from everywhere else. So it's very good at removing noise and extraneous activity from other sources. You also limit your search to frequency bands and time windows of activity, so you're limiting the complexity of this task of trying to block out other activity. And the other main thing you do is usually contrast power in bands between conditions, so you're isolating just the activity that is related to the task and task-related differences, so you can see subtle changes that way. It does have some difficulties near the center of the head based on some modeling, some of the math involved, so thalamus may be difficult, although I have seen people claim they've seen thalamus. And also highly synchronous sources, so if you have two say very almost perfectly synchronized sources, like say an auditory cortex, when you receive auditory input, you may have difficulty finding both, or at least finding the full strength of both of those sources. So here's an example of a dipole fit. This is from an auditory stimulus, and the classic large amplitude 100 millisecond response to an auditory stimulus in superior temporal gyrus. And so this is, you know ahead of time that there are probably two main sources of this activity. So you pick two dipoles and you fit them to your data, and you end up with those sources on the bottom right. It's hard to use this without poking it. So you end up with these two sources fitting this data. And again, this is what data in the CTF system would look like at the sensors. And you notice actually the activity is directly under this black mark here, which is 0. Remember how we said that the peaks are off to the side? So the peak activity is actually here and here in the channels. Again, why it's a little confusing. And then here and here for the other side. So this is actually field exiting the head and field entering. So you have a circle of current going like this around this location. And that's how you can kind of see it in the channels. This is MNE. So again, this is an auditory stimulus again, and you can see it localizing to superior temporal gyrus. But they fit all of their data onto the cortex, so it does localize it there. But if there was anything from another region, it wouldn't find it. And this is a SAM example. This is from a working memory task, and it's from a project where we're comparing it to fMRI for the same subjects and the same experiments. A working memory 2-back versus 0-back memory task. So 0-back's more of a control with no memory component. And you can see that with SAM we can localize, this is beta desynchronization, so it's actually a reduction in a beta oscillation, which is 15 to 30 hertz. And you see it within a particular window, which we think is related to memory updating, about 500 milliseconds centered on a response. And you see something similar to the fMRI. You can see source localization is not as good, but so why would you do MEG? Obviously fMRI is very good for source localization. Well, we've gained some extra information here. We know when this activity happened, within a 500 millisecond window at least. And we know what type of activity it is. It's a beta band desynchronization. So we've gained a little more knowledge about this task from doing MEG. And make a final point about SAM on the side here is that one reason it's good for seeing deep sources is that at every voxel you're typically generating a contrast between activity and an active and a control condition. So as long as there's a difference in those activity levels, it doesn't matter the absolute strength. So even if you have a weak source with depth, as long as there's a change related to your task, you're still going to see it. Now, let's go. Any questions on that part? I'm going to go through some other things you aren't supposed to see besides the deep sources. So there are some other things that people claim to not have seen, and again, for similar reasons, historical reasons and other things. And one of the main ones is radially oriented sources, and I'll go through all of these in turn. Some is that you might have anatomical cancellation of sources, or you may have a lack of an anatomically appropriate setup, like with the pyramidal cells. Or one thing that people claim you couldn't see is neuronal spiking, that you could only see dendritic input to cells, but we're at least seeing some very recent information that you might be able to see that, although that's still very preliminary. So the first of these assumptions about MEG that is probably wrong. So I've seen this, and again, this is from an old textbook. You can see at bottom here, they actually see what they say. Not seen on MEG, seen on EEG. This is often the way these things are presented in textbooks. It's just very much a black and white, and it's simplified for a textbook kind of a, that you can see this, you can see that, you can't see this. So the idea is that in order for a field to escape the head, you would need, for MEG, you would need what's called a tangential source, meaning tangential to the skull surface, which would usually be in a sulci in the cortex, so that the magnetic field surrounding that source would exit the head, right up here. Whereas in a radial source, well, the field is going to be rotating this way and may not exit the head, but really what they mean is it doesn't exit the head directly above the source. It will exit the head somewhere. It will exit the head over here and over here. It'll be weaker by the time it gets there, but it'll still be there, and so you can still see it. The other issue with this type of false dichotomy is that nothing is perfect. I mean, very few sources are perfectly tangential or perfectly radial. you have lots of orientations in between, and of course you will see at least part of that activity. Say you had one on this corner here, you would see a big signal this way, but maybe this part of the signal wouldn't be picked up or would be very weak on the other side of the head. And this is an example of where a lot of this this knowledge, quote unquote, came from, is that in the early days of MEG you would have these very few channel systems, and they would actually stick them on a part of the head where they expected to see the activity. So they would stick it directly over auditory cortex if they were playing sounds, and if they didn't see it, well, then you can't see it with MEG. Well, you can with a modern system like we have. It just escapes the head somewhere else. Any questions on that? Another thing that people claim would cause a lack of MEG activity is anatomical cancellation. So if you have dipoles facing each other across some piece of cortex, then the sources may cancel each other out, and you wouldn't be able to see them because the magnetic fields would be rotating different directions, and they would cancel each other out mathematically and never escape the head. So the big one that people thought you couldn't see in the very beginning was SMA, bilateral supplementary motor area, because you have simultaneous activity along the midline, and that activity is facing itself across the midline on bilateral cortex, and then it would cancel out. But of course in the cerebellum as well, you have these sulci type things in the cerebral cortex. If you have activity on each side of the sulci, of course, nothing perfectly cancels. They aren't directly on top of each other, so there will be some part of that activity that doesn't cancel. It might be reduced in amplitude, but it's still going to be there, but at lower amplitude. And of course, anatomy isn't always perfect. These things aren't necessarily going to be perfectly pointing at each other exactly at the same time. So there may be some issues here, but it shouldn't. Again, it's taken to the extremes of saying you just can't see these things. You can. It's just there is some effect of these issues. Another thing that people say is that you can't see any anatomy besides what we talked about in the beginning, which is the apical dendrites of pyramidal cells. So if you don't have a column of parallel dendrites receiving input at the same time, then you just can't see it. The amygdala is a big one. People claim you could never see that because you don't really have that sort of structure. Hippocampus might be okay. It's a little more columnar. Cerebellum, you can see the dendritic tree is quite complex for the major cells, so maybe they would get lots of cancellation there. But again, it's one of these false dichotomies. The opposite of perfectly parallel isn't completely perfectly random. All cells have some sort of structure that is not random, and you're going to get a net current of some sort. Again, it might be weaker than if you had perfectly parallel cells, but the activity is still going to be there. So it's a bit of a strong dichotomy that people use. Nothing is perfectly random in nature, so the chances of perfect cancellation of your signal based on anatomy is very low. And the other thing that people claim you can't see because of a very low amplitude and also cancellation is neuronal spiking, and this is still, I would say, under debate, although we're starting to see activity that looks like what it does with intracranial recordings. And intracranial recordings, a strong part of the signal is what is spiking activity that is in a high gamma range, so very high frequency, maybe in 100 hertz range. And you see this fuzzy activity without a clear peak at any one frequency band. But it was assumed in MEG that you would get cancellation. Any axonal activity, you get activity flowing in two different directions, and that activity should cancel out. But again, maybe there's not perfect cancellation, or maybe you're seeing activity on maybe the very beginning of the spike or something else. We're not quite sure yet, but it may be possible to see it, and people are starting to see some evidence thereof. And I'll show you some of that in a bit. So here's some examples. Any questions so far? So here's some examples from researchers here at NIH. Other people have been doing this, of course, but we're just going to brag about ourselves for a bit. So these are some of the areas that people have seen in their research, and then the last one is high gamma, which may or may not be spiking. So here's one. This is actually the first subcortical paper that we got published, and took a while to get it done because, again, a lot of reviewers will say, well, you just can't see deep sources because I read it in my textbook, so I'm not going to publish your paper. So it was difficult to get past that wall of people not understanding what we were seeing. But this is using effective priming, so they had words of various affect, and they were able to see, in this case, amygdala activity peaking at 150 milliseconds after a negative word. So again, another reason why why do you want to go through all this trouble of trying to find these weak sources in MEG? Because one reason being that we can try to better localize when these activities are happening, more so than you might be able to do with other technologies. This is another amygdala one. So this is during a working memory task, and so coherence between amygdala and cingulate predicted antidepressant response in ketamine. So this was you can see on the localization in the picture, and then the coherence or the correlation with antidepressant response in the graph below. Hippocampus, this was a spatial water maze, a virtual spatial water maze, and so they were having to remember where a platform was, and they had to search for that platform they remembered, kind of like the rat tasks. And so the hippocampal activity during the navigation correlated with the time to target. So if you had more hippocampal activity in the theta band, it took you less time to find the target. And they also found some overall differences between patients and controls. This is basic ganglia. This is very recent work, driven by our illustrious Erda, Linnea. And she came up with a gambling task to study reward processing. And so this is a map, a SAM map, of the difference between a high positive reward and a loss in a gambling task. And you can see left putamen activity during the reward processing peaking, I think, about 250 milliseconds at that, where that peak is on the right. So this is pretty exciting work. This is the first time we've claimed to have seen, or I think we are seeing, basic ganglia, which is exciting for a lot of different tasks with patients and normals. Here's a cerebellum example. This is finger tapping and the brain of our director, Allison Nugent. Recording done by another staff scientist, Tom Holroyd, and then the analysis by Stephen Robinson, another staff scientist with us. So this is one subject finger tapping at the self-paced, and you can see cerebellar activity peaking at a certain time relative to the finger tap. So, and it's on the correct side of the cerebellum for finger tapping. It's on the ipsilateral side. So, pretty confident that we're seeing that. And here's another one from this is a visual motor coordination task, one that we're running right now. So this is we're using a joystick to reach a target on a screen, and you can see high gamma activity, which we'll talk about more in a minute, during the actual reaching behavior in the cerebellum and also in posterior midline. So this is kind of a three for things we're not supposed to see. We can see the cerebellum, midline activity, which is supposed to cancel, according to some people, and also this high gamma, which may mean spiking, which wasn't theorized to be able to be seen with MEG. So high gamma, this is what it looks like in an MEG experiment. This is just published recently. This is a working memory task. Again, the similar one to we saw previously in the first example of SAM, where you have 2 back and 0 back in an N-back task, and then you also have rest as a control. And you can see a power spectrum. So this is just the frequency content of the channels. So you take all the MEG channels and say what frequencies are in there, and then what differences are there in the task. And you can see, you can see alpha activity here, peaking about 10 hertz. More at rest. This is a common phenomenon in MEG where alpha and beta will actually go down when you're performing a task. So this is 0 back and then 2 back. So the activity reduces. So you actually see the kind of counterintuitive, but some of these bands, some people consider them resting bands, and then they're broken up when you're actually performing the behavior. The opposite, though, happens at this high frequency band, we're calling high gamma. You see at rest you have a lower activity, and then it goes up with the task. And this is a zoom in of just that section, and you can see rest, 0 back, and a little bit higher at 2 back. You can see it's a very low signal. Probably again why it wasn't seen in earlier days. This high gamma activity is very low amplitude. It often wasn't even recorded. The early people again assumed you couldn't see it, so they would cut off the recording frequency at a lower rate where you couldn't even possibly see it. And it doesn't look like the typical bands where you have a peak at a single frequency. It's a broad, flat spectrum, but that is exactly the same kind of spectrum you see in internal recordings that represent spiking. So it may be a reflection of that, possibly. So here's a SAM source analysis of that exact same activity from the previous slide. So you have the alpha. What does it look like when you compare 2 to 0 back? You can see blue means a reduction in activity, so there's areas where we refer to that as desynchronization, meaning an increase in activation there, but it's actually indicated by a reduction in that frequency. And then you see the beta band, and at the bottom the high gamma band, which is in slightly different areas. It doesn't overlay exactly, so it does appear to be showing something slightly different about the processing during this task. So in summary, what have we learned? Theory doesn't always match reality. I think a lot of this knowledge was based on these theories about what you're seeing about MEG, and then assuming the theories are more real than they really are. The theories certainly predict what you would see in a strong sense, but not necessarily all you can see. We've also improved, or well, not me personally, but the MEG has improved technologically and with methods so that you can see weaker signals, both because the technology is better and our methods for seeing them are better. And we're also looking for them. Part of this is just that you have to decide to look. People thought you couldn't see it before, so they didn't bother looking, but now we are. But I think beliefs are sticky. Part of it is just because people, maybe saw that line in a textbook 20 years ago and they've never done MEG since, so that's understandable. But you keep people repeat and you still hear it, that you can't see deep sources with MEG and so on. But I think there's also this kind of tendency to prefer a black and white, a simplistic statement. EEG can see this, MEG can see that. You can't see radial sources, you can see tangential and so on. And the hardest one is can't over kind of hard. Deep sources are indeed difficult to see, but it doesn't mean you can't and you shouldn't try. And it's certainly a worthwhile endeavor because these areas of the brain are very important for what we study here. So, thank you very much. If you have any questions, grab a mic. If not, that's fine too. Thanks, and I'd like to thank our team, Allison, who's here, our director, and Tom and Steven. And I'd like to highlight Anna, our new lab manager. She's new to us, but she has a lot of experience at the MEG lab at the University of Maryland. So if you see her around, ask her for help. If any of you are running tasks, she'll be down there and helping out. And then Linnea, who's here as well, who saw that wonderful basic ganglia research, and our summer student. We have a website where you can go and find more information about all of this, and you're welcome to email me. If you email us, you can also join our mailing list or Slack page. And we do have a journal club once a month, and you can sign up for that if you get on the mailing list to hear about that, to hear more about MEG. So, thanks again.